Hello. Today we'll discuss pigeonhole principle, and then we'll discuss the pumping lemma, and we'll give some examples. So first we'll discuss the pigeonhole principle. What is basically is this? Pigeonhole principle says that if if we put in object into m boxes and if n is greater than m, that means number of object is greater than the number of boxes, then what will happen? Then at least on box must contain or must have more than one item in it. So this is the pigeonhole principle. That means if we have n objects and m number of boxes, and if we want to put this n object into the m number of boxes, and obviously the number of object is greater than the number of boxes, then at least one box must have one box must have more than one item in it. Now this pigeonhole principle is applicable to pumping lemma. Now we'll discuss what is pumping lemma. Pumping lemma is basically used to prove certain sets are non-regular. So now we'll discuss what is a pumping lemma. So pumping lemma pumping lemma. So pumping lemma, suppose or let L be a regular set. Regular set. L is any language, basically it is a regular set. Then there is a constant n such that if z is any word or any string, z is any word in L, that means z is any string or any word in this language L, and length of this word or length of this string is greater than n. So we may write z in this form, z is equal to u v w, in such a way that together length of uv is less than or equal to n, and alone v or length of v is greater than 0 or greater than or equal to 1, and for all I greater than or equal to 0, u v or I w is in language L. So this is basically the pumping lemma. Means if we have, suppose L is a any regular set, and there is a constant n, we may consider that n is the number of state, such that if string z is any word in L, within this language L, and the length of the string is greater than this constant n, so we may write z in this form UVW. That means we may partition this string into three parts, U, V and W, in such a way that together UV, that means length of UV together is less than or equal to the constant n, and alone length of V, that is alone length of V greater than 0 or greater than equal to 1, and for all I greater than equal to 0, for any integer I greater than equal to 0, U V power I W is in the language. Now the concept is very simple. Suppose suppose we consider that Z is any word or any string is of the form, suppose A1, A2, or suppose AM, where M is greater than N. Now this M, okay, so how this string will be accepted by the automata, A1, A2 up to AM. So obvious concept is starting from Q0, after reading A1, it may go to some state Q1, and from Q1 after reading A2, it will go to state Q2 and so on, right? So after reading AM, it will go to some state, suppose QM. So graphically we can say, suppose it is a Q0, and after reading suppose A1, and it will go some state, suppose QI, and after reading it will go to some state, final state, which is the accepting state, it is a QM, right? So initially after reading Q0, initially starting from Q0, after reading A1, you go to state Q1, and after reading A2, Q2, and finally after reading AM, we will reach QM. So now A1, A2 up to AM is accepted by this automata, and now concept is, if M is greater than N, if M is greater than N, N is the number of state, M is the length of the string. So obviously there are M plus 1 states. How many states will be there? There are M plus N states. So there are M plus 1 states. Now suppose this finite state automata, or suppose DFA has N states, that is number of states. So this L or L is accepted by a machine having n number of states, because L is regular and it will be accepted by finite automata, and this automata DFA has n number of states. So L will be accepted. So L is language will be accepted by the DFA having n number of states. But we have M plus 1 state here. Yeah. So M plus 1 state, but the DFA has n number of states. So M plus 1 states. So there are M plus 1 states, but we have n states of DFA, right? So here is the application of Pigeonhole Principle. That means number of object is greater than the number of states. So by Pigeonhole Principle, by Pigeonhole Principle, some state, some QI and some QJ state will be equal. That is, QI is equal to QJ. That means if this M is greater than equal to M, but we have n number of states, so the DFA having n number of states, but your string length is M, so it requires M plus 1 states. That means some state. So after Q0, reading A1 go to some Q1, and after reading A2 it will go to Q2, and in this way it will traverse from q0 to km, but some states where qi is equal to some state qj according to the pigeonhole principle. Now, now that means some qi, that means here a to this etc. after some state qi will be qj, because here also we consider that I is greater than j, right? So now we redraw this graph. It will be look like this. Suppose q naught, okay, starting from q naught, after reading a1 a2 up to ai, it will reach some state qi, right? And in qi, because we have mentioned that some states qi is equal to some states of qj, right? So in this states we partition the state like that: a I plus 1 strings, a length ai plus 1 to aj will be traversed here, so that qi is equal to some state qj, and from this states, after reading aj plus 1 to am, it will reach some state that is a qm. Okay, so now, so again I repeat, after reading a1 to ai, you go to state qi, and after reading ai plus 1 to aj, you are in the state qi, or we can say the qj, because these states are same. And after reading aj plus 1 to am, you go to state qm, and that string will be accepted. So from this diagram we can also conclude that a1 a2 ai aj plus 1 am will be accepted by this, will be accepted, because a1 a2 up to ai, after reading this you will go to these states, and from here after reading aj plus 1 to am string, it will go to state qm, accepted. So this will be accepted by this automata. If this will be accepted, so we can also write a1 a2 then ai, okay, and ai plus 1 to aj power of I, aj plus 1 to am will be also be accepted, will also be accepted. And we say that this path, so we can say that this is the path, you traverse this path any number of times. So you traverse this path any number of times. So you traverse this path any number of times you want. Okay, so this will also be accepted by this automata. So this will also be accepted, will be accepted, right? So now we can say that this part we consider that is u, and this part we consider it is v, and this part we consider it is w. Clear? Now what is the meaning of this? So when the string u is applied, it reaches to state qi, we also say that qj. Now on application of v, it remains in the same state. Qi is equal to Qj. Therefore, after reading or after application of the input W, we will reach to the state Qm. And V is a state we can apply this string any number of times. So here it is I number of times, where this I is greater than or equal to 0. Clear? So now we can say that this u v to the power I or v power I w belongs to the language L. Clear? Now, why this pumping lemma will be used? Pumping lemma is basically useful for showing that certain sets to be non-regular. So this is basically useful. So this is useful for showing that certain sets to be non-regular. Clear? Now, how we can prove that certain sets to be non-regular? So we have to follow some steps. So now using this pumping lemma, we can prove that certain sets to be non-regular. So pumping lemma steps. Pumping lemma steps. Right? Number one, we have to assume that L is regular. Initially, we have to assume that L is a regular, and let n be the number of states. Number of states in the corresponding finite automata. Yeah. So number two step, choose any string or choose a string, let it is Z, such that mod of or length of that string is greater than n. This is Pigeonhole principle. And use pumping lemma to write, that is, we know that pumping lemma we can partition the string into three parts, u, v, w, in such a way that together u, v should be less than equal to n, and mod of v, that length of v, alone greater than 0 or greater than equal to 1. Now step 3, we have to find, so find a suitable integer I such that u v power I w does not belongs to the language L. So initially we have assumed that L is regular, and after some steps we show that this string does not belong to the language. So this contradicts our assumption. So this contradicts our assumption. Hence, hence we can say that L is not regular. So this to prove certain sets are non-regular, we have to follow these steps. 1, 2, 3. Initially, we have to assume that L is regular. Then we choose any string Z such that the condition is the length of this string will be greater than n. N is the number of states. Then we have to apply the pumping lemma, and we partition this string Z into 3 parts UVW. In such a way, we have to partition that length of the UV together less than equal to n, and alone length of string V greater than 0. And we have to find then a suitable integer such that this will not belong to the language. V power I W does not belong to L, and this is basically the contradiction of our assumption that L is regular. So this is the contradiction, so we can say that L is not regular. Now we'll show some example. First example, suppose we have to show question 1. Question is show that L equal to 0 to the power n and 1 to the power n such that n greater than or equal to 1 is not regular. That means there is no finite automata which can be designed or drawn that it will accept same number of 0 followed by same number of 1. So now we can solve this. How? So solution. So by pumping lemma we can write that Z is equal to 0 to the power n and 1 to the power n. What is the meaning of this? It means 0 0 0 and 0 0 0. Also we can write 0 0 0 and then 1 1 1 dot dot, it is 1 1 1. That means we can partition this. We assume that Z is equal to, so assume initially we assume that L is regular. Clear? Initially we have to assume that L is regular, right? Now we have chosen string that we assume that the string is 0 to the power n, 1 to the power n, and we obviously the length here, obviously the length of this string Z will be basically 2n, which is greater than n, right? So it is basically, we can say that length of string is basically 2n, which is greater than n. Now we can partition Z in such a way. Okay, we partition the string in such a way that from the first part, from 0 part, we partition the string in this way. Suppose this will be 0 n to the power 0 to the power n minus k, and from here to here we assume that it is 0 to the power k, and from here it is, we assume that 1 to the power n. So we can write the string is like that, n to the power k and 0 to the power k and 1 to the power n. We partition this in this way. Now what is u? We assume that u is equal to 0 to the power n minus k, and we assume that v is equal to 0 to the power k, and w is equal to 1 to the power n. Now the constraint is that together uv or length of uv should be less than or equal to n. So from here we see that if we take this string ub together, the length of the string will be n. So we satisfy this condition, and alone length of v should be greater than 0. So here v should be greater than 0 when k is greater than, here k is greater than or equal to 1. Then obviously v is greater than, length of the string is greater than 1, and w is equal to 1 to the power n. Now using pumping lemma, so using pumping lemma we can write z is equal to 0 n minus k 0 k I and 1 to the power n. It also belongs to the language, but for I equal to 0, but for I equal to 0, what will happen? Here it will be z, it will be, when I equal to 0, this part will be length of string 0, that means epsilon, so it will be n k and 1 to the power n. But as the string is of the pattern same number of 0 then followed by same number of 1, now the string here 0 to the power n minus k 1 to the power n, these are basically not satisfied this condition, means n, that is n minus k, which is never equal to n. Why? Because k is greater than or equal to 1. Right? So this is basically contradiction. So which is a contradiction? Which is a contradiction? That is 0 to the power n minus k and 1 to the power n does not belong to the language L. Hence L is not regular. Another example, suppose prove L equal to a to the power n b to the power k such that n greater than k greater than or equal to 0 is not regular. So the procedure is, we have to assume L is regular, right? Now we assume or let z is any string of the form a to the power n b to the power k is basically of the form u v w. We can partition this such that in such a way that mod of u v is less than equal to n, mod of v alone greater than 0 or greater than equal to 1. Then by pumping lemma, we can write z is equal to a to the power n b to the power k is of that form a to the power k a to the power n minus k and b to the power k, right? So it means we assume that it is u and we assume that it is a v and we assume it is a w. Now look, uv length which is basically equal to n here, clear, k cross, then it will be n, the whole, which is basically satisfied the condition of n alone v which is greater than 0. Here it is the length of this string is n minus k. Here length of the string is n minus k, where k is greater than here the length alone v should be greater than or equal to 1. That means the length, because k is greater than 0, so that means it will always greater than 0. Length of v will be greater than 0 and w is equal to b to the power k. Now for I, so according to Pigeonhole principle, that this should belongs to the language, means a to the power k, then a to the power n minus k of I and b to the power k should belongs to the language L. But for I equal to 0, what will happen in this string? So it will be a to the power k and b to the power k. But the pattern or the question is that n is greater than k and k is greater than or equal to 0, right? So k can be, oh, here k can be get 0 also. So now here, if k is equal to 0, then obviously length of v will be greater than 0. No problem here. So k is greater than 0. Here we have assumed that k is greater than 0 as per the question. So now n is greater than k. Obviously n is greater than k. So here both of the strings are same length, means same number of a followed by same number of b. But for question it is basically contradiction, because number of a should be greater than number of k as per our question. As per our question, number of a should be greater than number of k. There cannot be same number of a followed by same number of b. So hence it is a contradiction. So a to the power b to the power k does not belongs to the language. So or hence L is not regular. Now we will give another example in different way. We can also give some other example in different way. Suppose example 1, suppose we are given this language L is equal to a I 2, where I is greater than or equal to 0. So now from this pattern, what is basically language is? We have to prove that L is not regular. We have to prove that L is not, so is not regular. Right. Now what is the language pattern? So it will be like this, that when I equal to 0, so a to the power 0, that means string will be epsilon. Then when I equal to 1, it will be a. When I equal to 2, a, and so on in this pattern. Right. So as per the principle of pumping lemma, that we have to assume that L is regular. So assume L is regular, right? And we assume also let Z is any string as of the form a n 2. So what is the length of the string? So length of the string, which is basically n square, and obviously greater than n is the number of states of the DFA. So it is greater than. So first condition is satisfied. Now Z can be written as UVW such that mod or length of UV is less than equal to n, and mod or length of V alone greater than 0 or greater than equal to 1. Then for all I greater than or equal to 0, U, V, I, W should be belongs to the language L. This is pumping lemma principle, pumping lemma actually basically. Now, if U equal to epsilon, U may be any string. So we assume that U is a string of length 0, that is U is equal to epsilon. So from here, if U equal to epsilon, so what will be V? So obviously length of V should be less than equal to n. From this, right? From this we can say length of V is less than equal to n. So we can write that 0, because condition is V length of string greater than 0. So this is V, and obviously it is less than or equal to n. V greater than 0, that's why we have written this, and obviously mod of length of V less than equal to 1, so we also write this. Okay. Now we can write this n square, we add n square on all these sides. So 0 less than n square or length of V, so which is also less than or equal to n square, n, we add this term everywhere. Now it basically implies that n square less than n square or length of V are less than or equal to n square or n, which is also implies that n square. So this n square means length of the string, that is z, that is length z. What we have assumed that z is any string of the form uvw. Z is any string is of the form uvw, right? So we can write here that n square is basically u, v and w, its length, and alone v is this, which is also less than equal to n square or n. Okay, so as we have assumed that z is equal to ubw, so n square also, this it also implies that z is this, n square, length of this, basically length of this is equal to n square. So mod of z or length of z is basically, or n square is basically, we can replace by length of z, and length of z is basically, we can say, mod length of ubw. So that's why we write in this form. So now n square less than length of u v2 w, right, which is less than or equal to n square or n. So this can be also written as, n square less than u v2 w, which is also less than or equal to n square or n, and this quantity is basically less than n plus 1 square. Now look, it basically says that there is a string which belongs to this, means there is a string which belongs to n square and n plus 1 square. But in practically, from this language pattern, a to the power I to the power square, so from this pattern no string can be of this form between n square and n plus 1 square. So this basically does not belongs to the language. Clear? So u v2 of w does not belongs to language L. So hence L is not regular. Clear? Because if we choose n equal to 2, so string of length will be 4, and if we choose n equal to 2, then it will be n plus 1 means 3 square, that means it will be 9. So no string length will be in this gap 4 and 9. From here also look, it is a 4, and when I equal to 3, when the value I is equal to 3, so it is basically I equal to what, I equal to 2. So then next string will be I equal to 3. So when I equal to 3, so 9, so a to the power 9 means 9i, so it will be 9. So there will be a string, it will be of length, the length of the string will be 9. So here it is basically when I equal to 2, so length of the string will be 4. So no string belongs within this range 4 to 9. But here it says, here basically it says that there is a string which belongs to this, which is contradiction because it does not belongs to length of this u v to w does not belongs to the language L. Hence we can say that L is not regular. So in this way there are other proof also. So thank you.